Hello everyone and welcome to our channel, MooTechie. It's wonderful to have you here as we dive into the fascinating world of amino acids. These tiny molecules are the true building blocks of life, and understanding them is the first step to mastering biochemistry. So let's get started. What are amino acids? They are the fundamental monomers that link together to form proteins. Each one features a common backbone and a variable R group. Did you know there are 20 standard alpha amino acids naturally coded by genes and living organisms? It's these distinct side chains that drive their classification and determine their specific chemical properties. Now imagine a polypeptide chain, where amino acids like serine, leucine, alanine, and glycine link together in a specific order to form all the functional proteins your body needs. Now let's move on to the general structure of an amino acid. At its heart is a central alpha carbon, bonded to 4 distinct groups, forming the core structure. The standard backbone consists of an amino group, a carboxyl group, and a hydrogen atom. What makes each amino acid unique is its variable R group, or side chain, which determines its specific identity and properties. And in nature, they almost always exhibit an L configuration chirality, with the exception of glycine. Next, we explore the backbone and the peptide bond. Amino acids link together via a peptide bond, which is formed through a dehydration reaction, releasing a molecule of water in the process. This creates a repeating backbone pattern along the protein chain. N, C, C, N, C, C. This chain has a specific directionality, running from the N terminus, which is the amino end, to the C terminus, the carboxyl end. Visually, you can think of one amino acid with its structure H2N-CH R-C double bond O-OH. After a dehydration reaction which releases H2O, it forms a peptide bond with another, resulting in H2N-CH-R-C double bond O-NH-CH-R-C double bond O-OH. The backbone pattern is simply N connected to C alpha, connected to C, and so on. Coming up, we'll discuss the zwitterion concept. At physiological pH of around 7.4, amino acids exist predominantly as a zwitterion. This means they contain both a positive NH3+ group and a negative COO- group, creating a net zero charge. It's fascinating how the pH of the environment strictly controls the protonation state of these groups. So an amino acid can shift between its neutral form and its zwitterion form at pH 7.4, where it has a net charge of 0 through a simple process of proton transfer. Following this, let's talk about essential amino acids. There are 9 of them classified as essential because they cannot be synthesized by the human body and must be obtained through dietary sources. The list includes histidine, abbreviated HSH, isoleucine, ILE or I, leucine, LEU or L, lysine, LYS or K, and methionine, MET or M. The list continues with phenylalanine, PHE or F, threonine, THR or T, tryptophan, TRW or W, and valine, VAL or V. These must be consumed via foods like meats, eggs, dairy, or specific plant combinations. Now, what about the ones our body can make? Let's look at non-essential amino acids. There are 11 of these classified as non-essential because they can be synthesized by the body and are not strictly required from the diet. The list includes alanine, ALA or A, and then arginine, which is often conditionally essential, ARG, R, asparagine, NS or N, aspartic acid, ASP or D, and cysteine, CYS or C. We also have glutamic acid, GLUE, glutamine, GLNQ, glycine, GOYG, proline, PROP, serine, SERS, and tyrosine, TYRY. These are synthesized via various metabolic pathways, like glycolysis and the citric acid cycle. As we continue, let's understand the R group classification overview. The 20 amino acids are categorized into 5 major groups based on the chemical nature of their side chains. We have the nonpolar aliphatic group, with examples like glycine and alanine, the aromatic group with phenylalanine and tyrosine, the polar uncharged group with serine and threonine, the acidic or negatively charged group with aspartic acid, and the basic or positively charged group with lysine and others. So the categories are nonpolar aliphatic, aromatic, polar uncharged, acidic negative, and basic positive. Let us now look more closely at nonpolar amino acids. These have hydrophobic R groups that lack charged or electronegative atoms. They tend to cluster in the interior of proteins to avoid water. The aliphatic members include glycine, which is the smallest, alanine, valine, leucine, isoleucine, and methionine, which contains sulfur. We also have proline, which has a cyclic structure, and tryptophan, which is the largest in this group. The aromatic member we'll highlight is phenylalanine. Moving forward, we'll see the polar and charged amino acids. These groups are hydrophilic, interacting readily with water. Their charged side chains play crucial roles in protein stability and enzyme active sites. The polar uncharged group includes serine, threonine, cysteine, asparagine, glutamine. The acidic or negatively charged group includes aspartic acid and glutamic acid. The basic or positively charged group include lysine, arginine, and histidine. Now let's summarize some key physical properties. Amino acids are typically white crystalline solids with high melting points, often over 200 degrees Celsius, due to strong ionic forces in their crystal lattice. They're generally water-soluble and insoluble in nonpolar solvents, though solubility can vary a lot depending on the R group. And all amino acids except for glycine have a chiral alpha carbon and exhibit optical activity, meaning they can exist as L or D isomers. Next, we explore their chemical properties. Amino acids are amphoteric, meaning they can act as both acids and bases, capable of donating or accepting protons. As we know, at physiological pH, they primarily exist as zwitterions. Their specific pKa values for their functional groups determine their ionization state at any given pH. And importantly, cysteine residues can oxidize to form strong covalent disulfide bonds, creating cysteine and adding great stability to protein structures. Let's visualize the pH effects on charge. In a low pH, acidic environment with excess H+, the amino group is protonated to NH3+, and the carboxyl group is COOH, giving a net positive charge of +1. At the isoelectric point, or pi, we have the neutral zwitterion form with NH3+ and COO- for a net charge of 0. In a high pH, basic environment with a deficit of H+, the amino group is NH2 and the carboxyl group is COO-, resulting in a negative charge of -1. The Henderson-Hasselbalch equation guides precise buffer calculations and titration curves. Side chain pKa values can shift the isoelectric point, creating unique charge profiles for each amino acid. The environmental pH directly determines whether these groups are protonated or deprotonated. Finally, let's bring it all together with a summary. Amino acids share a common backbone featuring an alpha carbon, an amino group, a carboxyl group, a hydrogen, and the unique R group. Their classification is driven by R group properties, whether they are nonpolar, polar, acidic, or basic, and by nutritional necessity. Their key properties include zwitterion formation, amphoteric behavior, specific pKa values, and a characteristic isoelectric point, or pi. So from their fundamental structure to their diverse classes to their unique properties, amino acids are truly remarkable. Thank you. See you in the next class. Author MooTechie.